In 2020, a dead star 30,000 light-years away fired a burst of radio waves that lasted less than a millisecond. Astronomers measuring its energy found it had released as much power as our sun produces in 30 years, in half a thousandth of a second. It was unlike any signal ever traced to a confirmed source, and it may have just cracked open one of the biggest mysteries in modern astronomy. I'm Nick, and you're watching Astro X. Join me today as we unravel the mystery of the most magnetic objects in the universe. Objects so extreme, they may hold the key to some of the most baffling signals ever detected crossing the cosmos. Astronomers had been puzzling over fast radio bursts, FRBs, for over a decade. These are intense, millisecond-long flashes of radio waves that arrive from apparently random directions across the sky. The first was spotted in 2007, buried in archival data from the Parkes Radio Telescope in Australia. By 2020, thousands had been catalogued, arriving from billions of light-years away, each one brilliant and fleeting. Not a single one had ever been traced back to a confirmed source. They typically come from known objects with known physics, but not FRBs. An FRB appears, blinds a telescope for a millisecond, and vanishes. No repeat, no return address. Then, on April 28, 2020, something changed. A magnetar inside our own galaxy, designated SGR 1935+2154, suddenly erupted. Multiple radio telescopes across the world caught what came next, a burst of radio waves roughly 1 million times more powerful than any radio emission ever recorded from within the Milky Way, in under a millisecond. If that magnetar were placed 500 million light-years away, roughly where many known FRBs originate, this burst would have looked almost identical to a fast radio burst, essentially indistinguishable. So what is this object, and what does it tell us about the thousands of mysterious signals that have been arriving from the edge of the observable universe? To understand what makes this discovery so significant, we need to understand what a magnetar actually is and what makes it different from any other object in the cosmos. Magnetars are a type of neutron star, and neutron stars, as a reminder, are the crushed-up cores of dead supergiant stars, the densest objects in the universe that aren't black holes. A typical neutron star packs more than the mass of our sun into a sphere roughly the size of a city. If you could take the island of Manhattan and somehow fill it with nuclear matter pressed together until there was no space between anything at all, you'd have something approaching the right dimensions, except it would weigh over 1.5 times what the entire sun weighs. Neutron stars already carry magnetic fields trillions of times stronger than Earth's, but magnetars are something else entirely. Their magnetic fields are roughly 1,000 times stronger than a typical neutron star's and a quadrillion times stronger than Earth's. To call this extreme would be an understatement. Here is a way to feel the scale of that. If a magnetar were as far from Earth as the Moon, its magnetic field would erase every credit card on the planet. Move it to half the Earth-Moon distance, and it would begin to physically affect the iron atoms in your blood cells. The hemoglobin in every red blood cell in your body would be disrupted before you had any warning at all. These extraordinary fields are thought to arise in the first milliseconds of a neutron star's birth, when violent convection deep inside the collapsing stellar core amplifies the magnetic field to otherwise impossible levels. The result is the most magnetically intense object we have ever confirmed to exist, and it turns out they are not quiet. What magnetars actually do? Magnetars are not stable. Their intense magnetic fields place enormous stress on the star's solid crust, a crust made not of rock or metal, but of crystalline nuclear matter, 100 trillion times denser than steel, yet brittle in its own way. Imagine a tectonic plate made of that material. When the magnetic forces build beyond what the crust can bear, it fractures, just as the Earth's crust does in an earthquake. We call these events starquakes. When they occur, magnetic field lines snap and violently reconnect, accelerating charged particles to near the speed of light and generating massive bursts of X-rays and gamma rays. These are known as magnetar flares, and they are among the most energetically concentrated events in the universe. In 2004, a magnetar called SGR 180620 produced a flare so powerful it briefly outshone every radio source in the sky and ionized Earth's upper atmosphere from 50,000 light-years away. Not damaged it, not nudged it, ionized it. To call it powerful would be an understatement. The magnetar SGR 1935 plus 2154 had been known and monitored since 2014. Located in the constellation Vulpecula, roughly 30,000 light-years away, it had been producing typical magnetar activity for years. X-ray bursts, the occasional flare. Standard behavior for its class. Then, in April 2020, it woke up differently. Over the course of several days, it began flaring more frequently, more energetically. Both the CHIME radio telescope in British Columbia and the STARE-2 array in California were observing when, on April 28th, SGR 1935 plus 2154 emitted something entirely new. In 0.5 milliseconds, half a thousandth of a second, it produced a burst of radio waves with a brightness roughly 1,000,000 times greater than any previously known radio emission from within our galaxy. Two distinct subbursts arrived 29 milliseconds apart. The signal was bright, sharp, and precisely structured. And that specific structure, two subbursts separated by tens of milliseconds, matched the morphology seen in many confirmed extragalactic fast radio bursts. The resemblance was immediate. The resemblance was striking. Before April 28, 2020, every theory about what causes fast radio bursts was untethered. With no confirmed source, every candidate was speculation. The proposals ranged across neutron star mergers, cosmic strings, and, in a few imaginative corners of the academic literature, even more exotic explanations. Without a source, you couldn't test any of them. SGR 1935 plus 2154 provided the first anchor. For the first time, a source of an FRB-like burst had been observed in real time from a confirmed object at a known distance with telescopes already watching. This graph, plotting the radio burst brightness of known magnetar flares alongside known extragalactic FRBs, shows that the April 28th burst sits in the gap between the two populations. Not quite reaching the faintest known FRBs, but closer than anything we had ever measured before. This was not a coincidence. The community's consensus shifted rapidly. Magnetars were now the leading, confirmed candidate for producing at least some class of fast radio bursts. After over a decade of mystery, there was a name on the door. And yet, as is always the way, the more closely astronomers looked, the more the picture complicated itself. Loop 4. The repeating problem. Here is where the story deepens in a way that doesn't resolve cleanly. Most FRBs are one-off events. They appear once and never repeat. But a subset, perhaps 3 to 5% of all known FRBs, do repeat, and the repeating ones behave very strangely. The first repeating FRB ever found, designated FRB 121102, has now fired hundreds of times from a dwarf galaxy 3 billion light-years away. Its bursts cluster in time, switching on and off over what appears to be a loose 157-day cycle. Another repeater, FRB 2020-1124A, produced hundreds of bursts in just a few days before going completely quiet, then started again months later with no warning. If all FRBs come from magnetars, why do some repeat and others don't? SGR 1935 plus 2154's Great Radio Burst in 2020 was a single event. The magnetar has never produced a radio burst of comparable magnitude since. A source that fires once and goes quiet looks nothing like a source that is fired hundreds of times across years. The data does not fit together cleanly. The closer you look, the more the single elegant explanation starts to fracture. And this is precisely the point where this story becomes genuinely unresolved. Loop 4. The repeating problem. Here is where the story deepens in a way that doesn't resolve cleanly. Most FRBs are one-off events. They appear once and never repeat. But a subset, perhaps 3 to 5% of all known FRBs, do repeat, and the repeating ones behave very strangely. The first repeating FRB ever found, designated FRB 121102, has now fired hundreds of times from a dwarf galaxy 3 billion light-years away. Its bursts cluster in time, switching on and off over what appears to be a loose 157-day cycle. Another repeater, FRB 2020-1124A, produced hundreds of bursts in just a few days before going completely quiet, then started again months later with no warning. If all FRBs come from magnetars, why do some repeat and others don't? SGR 1935 plus 2154's Great Radio Burst in 2020 was a single event. The magnetar has never produced a radio burst of comparable magnitude since. A source that fires once and goes quiet looks nothing like a source that is fired hundreds of times across years. The data does not fit together cleanly. The closer you look, the more the single elegant explanation starts to fracture. And this is precisely the point where this story becomes genuinely unresolved. Theory 1. Standard magnetar flares. The leading theory remains that most FRBs are produced by magnetars during extreme starquakes or magnetic reconnection events. The SGR 1935 plus 2154 burst supports this. The flare drives a shockwave through the magnetar's magnetosphere, accelerating electrons to relativistic speeds and producing coherent radio emission via a mechanism called synchrotron maser emission. The issue is the energy gap. Not all magnetars are equal. Younger magnetars, formed more recently from a supernova, retain far more stored magnetic energy. A young magnetar with a field 10 or 100 times stronger than SGR 1935 plus 2154 could plausibly close the gap. The problem is that we haven't observed any such magnetar producing such a burst. We're relying on extrapolation rather than evidence. So while the magnetar flare model remains the best supported theory, it can only explain the full population of FRBs if we invoke a range of magnetars we haven't directly observed doing the things we need them to do. Theory 2. Magnetars in dense plasma environments. A second theory proposes that repeating FRBs come from magnetars sitting inside unusually dense plasma environments, perhaps orbiting near an active galactic nucleus or still embedded in the supernova remnant from their birth. Dense plasma surrounding the magnetar could amplify and shape radio emission through a process called plasma lensing, transforming otherwise ordinary bursts into the complex, recurring signals we see from FRB 121102 and its relatives. Astronomers have confirmed that several known repeaters do sit in environments with unusually high electron densities. The issue is fine-tuning. This model requires each repeating FRB to independently sit in exactly the right unusual environment. As the sample of repeaters grows, that coincidence becomes harder to defend without a systematic reason for why these magnetars end up in such environments. Theory 3. 2 populations, 2 origins. The most uncomfortable possibility is that we are not looking at one phenomenon wearing different masks. We may be looking at 2 genuinely distinct classes of events that happen to produce similar radio signatures. Non-repeating FRBs could be cataclysmic, one-time events, the merger of 2 neutron stars producing a kilonova, or the collapse of a massive neutron star into a black hole. events that emit a bright millisecond radio flash and then leave nothing behind. These happen once, they cannot repeat. Repeating FRBs, meanwhile, could be magnetars in unusual environments, producing flares over years or decades. The issue is that this model is philosophically uncomfortable. We like unified explanations. Two separate physical origins for what appears to be one class of signal is an untidy solution. It raises the immediate question of where the dividing line is, and whether intermediate cases exist that belong to neither category cleanly. So far, no one has been able to rule this out. In the end, it seems like no single theory can explain all fast radio bursts. What the SGR 1935 plus 2154 detection confirmed is that magnetars can produce FRB-like events. That is a major breakthrough, the most significant in FRB science since their discovery. But whether magnetars explain every FRB, the most powerful ones, the repeating ones, the ones in bizarre environments, remains genuinely frustratingly open. What we can say is this: before April 28, 2020, FRBs were signals without sources. Now they are signals with at least one confirmed source class. That is enormous progress. Scientists are already planning to dramatically expand the data. The proposed DSA-2000, an array of 2,000 radio dishes spread across the Nevada desert, would detect fast radio bursts at a rate of thousands per year, with precise enough localization to pin each one to a specific galaxy, a specific position within that galaxy. With that volume of data, the statistical patterns will become far clearer. Are all FRBs coming from the same type of environment? Do the repeaters cluster in a distinct class of host galaxy? Are the most powerful bursts systematically different from the weaker ones? The answers are not here yet, but for the first time, they feel genuinely within reach. When astronomers spent over a decade cataloging mysterious millisecond flashes from the far reaches of the universe, they were collecting a library they couldn't yet read. Each signal was a word in a language no one had the key to. Then, one dead star on the edge of our own galaxy cleared its throat, and in 0.005 of a second, the language just began to make sense. This is how science works at its most extraordinary, not always with a dramatic announcement or a press conference, but with one signal from one object in 1 millisecond, nudging open a door that had been sealed for a decade. When new data challenges our long-held theories this way, it can usher in revolutions in how we understand the universe. Whatever the full story of fast radio bursts turns out to be, we are certain to learn something about the cosmos that no human has ever understood before. Isn't that remarkable? What do you think is producing the most powerful fast radio bursts? Let me know in the comments below. Now, so far this video has covered the discovery that finally connected magnetars to fast radio bursts, arguably the most important breakthrough in FRB science in 15 years. But recently there have been detections of FRBs so rhythmic and layered in structure that some astronomers have proposed explanations that go well beyond magnetars entirely. To stay on top of these developments as we cover them, visit the link in the description to become an Astrum astronaut on Patreon, where you can watch videos ad-free, see your name in the credits, and submit questions directly to the team. Otherwise, click the playlist here for more Astrum content. I'll see you next time. How close would I need to be to a magnetar before it became dangerous? This is a genuinely fun question to sit with, partly because the answer is so unreasonable. A magnetar's surface magnetic field is roughly 10 to the 15 Gauss. For comparison, Earth's magnetic field at the surface is about half a Gauss. The magnets in a hospital MRI machine run to around 15,000 to 30,000 Gauss, strong enough that you absolutely cannot bring metal objects into the room without risk. You feel nothing from it personally, but it will fling a forgotten coin across the room. A magnetar's field is roughly 10 billion times stronger than that MRI magnet. Physicists calculate that at around 1,000 kilometers from a magnetar's surface, still what we'd call its near field, the magnetic forces would be strong enough to distort the electron orbitals inside atoms. Not rearrange chemistry the way heat or pressure does, physically deform the shape of the electron clouds that hold molecules together. At a few hundred kilometers, the distance between two cities, electrons and atoms would be squeezed into elongated needle-like orbitals aligned with the magnetic field lines. Ordinary chemistry would break down. Molecules as we know them couldn't form. The human body, which is entirely built on molecular chemistry, would cease to function as a coherent object. You would not feel it coming. There would be no heat, no pressure, no warning signal your nervous system could interpret. One moment you would exist, the next, the magnetic field would have restructured the fundamental architecture of your atoms. To call it lethal would be an understatement. The good news, if you need some, the nearest known magnetar is about 10,000 light-years away, so we have some margin.